So this lesson is on converting dv to spherical coordinates. And I just want to say that dz, dy, dx is not as simple as saying d rho, d phi, d theta. They're not the same. You cannot just substitute. We need to think about the geometry that's involved. So let's talk about dz, dy, dx. That, of course, is dv. Yes, the rate of change of volume is dz, dy, dx. Why? Where does that come from? We decompose our solids into little rectangular blocks like this, and we can find the volume of that one if we call this distance change in x, this one change in y, this one change in z. Then the change in volume, if we grow in that direction, the change in volume is simply change in x times change in y times change in z. Or if you like, dv is dx, dy, dz. And of course, the order doesn't really matter. More often than not, we say dv is dz, dy, dx. But if we're working in spherical coordinates, we don't break things up into little boxes. We break them up into little pieces, little shells. So let's take a look at an image of those shells. So looking at our picture here, we have an extension using the various spherical coordinate notation. So I have from this point out to this point, we have the spherical radius. Here's the center going to P and then growing some more. So this little blue line corresponds to the change in rho. So let's go ahead and include that. So the blue piece corresponds to the change in rho. So the blue piece is the change in rho. Now we have a couple other pieces we need to think about. But before we do that, let's remind ourselves of how we find an arc length. So what is an arc length for a sector? So just a quick reminder, I have an arc length. It has a radius, it has an angle, and that distance is the arc length. But the thing to recognize is that arc is a fraction of the circumference. What kind of a fraction is it? Well, that angle divided by 2 pi tells you how big the fraction is, times the circumference will give us the arc length. Now, we remember the formula for circumference. We take angle divided by 2 pi times 2 pi r, 2 pi radius, equals the arc length. So the 2 pi's divide out and you get the radius times the angle in radians equals the arc length. And in calculus, we just about always use radians. So radius times angle will get us the arc length. But I want to take a look at a couple other arcs on that image. So let's take a look and identify what those arcs are. So we had the blue one was change in rho. How about the red one? What will that red arc be? We've said it's the radius times the arc length. Remember, phi is measured down from the z-axis. If we follow this red arc, phi is changing. Here's my original one, and that's how it changes. So that angle is the change in phi. And the distance you can see here is rho. So this red arc will be radius times angle. The red arc will be rho times the change in phi. So let's go ahead and put that down there. The red arc is rho times the change in phi. But I have one more that I want to get. So let's take a look at that one and identify how we can figure that out. And that's this little green thing. So the little green thing is going to take a little bit more work to understand. So what is that little green thing? We can see the angle it's moving through is the change in theta. We can see the angle is the change in theta, but what is this distance? What is this distance? It is a radius, and in fact, it is the radius that is made with r that we did back in polar coordinates. So can you see that triangle? This is the z value, this is phi, this is rho, and that distance here, which is the same as this distance, is r. So let's look at that triangle that we established here again. Z is here, Phi is here, rho is here, and this thing in green is r. Looking at that triangle, z is here, phi is here, rho is here, and this is r. And then what do we know about r? R is what? Well, sine of phi is r over rho. So rho sine phi equals r. Now, again, our goal is to get the distance of that little green arc. So let's go back there again and look at that little green arc. What do we see there? Fine, this is r. We've established the fact that r is rho sine phi. The angle here is change in theta. We know that the arc length is radius times angle. R times change in theta will be green. So recognize that. Green is r times change in theta, but we just said r was rho sine phi, so this gets rho sine phi change in theta. So how about the change in volume? Now, this isn't perfect now, right? This isn't going to be perfect. What will the change in volume be? So let's go back again and look at our picture. This thing isn't quite a box, but if these things are small enough, it's approximately a box. So the blue times the red times the green should be an approximation for the volume of this box. So the blue times the red times the green, what do we get? Change in rho, rho change in phi, rho sine phi change in theta. And this will lead us to our dV that we need. What will dV be in the world of spherical coordinates? Notice rho squared times sine of phi, rho squared sine phi, and then what order do we typically go in? I think most of the time it goes d rho, d phi, d theta, although there's not a standard. But that's what we'll stick with. That will be our conversion to work in spherical coordinates. So let's use that to find the volume of a sphere. So we want to find the volume of a sphere with radius 2. And we recall from earlier on that volume could be triple integral of 1. Remember, typically a triple integral gives us a 4-dimensional volume, but it's a triple integral of 1 dz, dy, dx, or dv. We're going to go ahead and rewrite this in terms of spherical coordinates. And what did we say dv was? We're going to say the triple integral of 1 rho squared sine phi d rho, d phi, d theta. Now, if I have a sphere of radius 2, then rho has to range from 0 to 2. Now, let's think about the angle phi. So phi runs from the North Pole. Phi starts at 0 at the North Pole. And to get the entire sphere, how far does it have to go? Here's phi is 0. Here's phi is 90 degrees or pi over 2. Down here, phi is 180 degrees or pi. So phi goes from 0 to pi to get the entire sphere that we're working with. Phi goes from 0 to pi. And then how about theta to go all the way around? Again, let's look at our graph one more time. What does theta have to be to go all the way around? Theta is 0, 90, 180, 270, 360. Theta has to go 0 to 2 pi to go all the way around. And this is what we need to do to evaluate. So let's first start with the innermost inner integral. From this perspective, sine is a constant. The integral of rho squared would be rho cubed over 3. As rho goes from 0 to 2, if rho is 2, 2 cubed is 8, 8/3 sine phi. Seems to be my answer. So it's 8/3 sine phi. Minus 0 if rho is 0. So my innermost inner integral is 8/3 sine phi. Now let's work on the inner integral. The antiderivative here would be negative 8/3 cos phi. Evaluated as phi goes from 0 to pi, which is negative 8/3 cos pi minus cos 0. Which gives me negative 8/3. Cos pi is negative 1 minus cos 0 is positive 1. That gives me negative 8/3 times negative 2, or 16/3 for my inner integral. And let's finish off the integral. So this is 16/3 theta, as theta ranges from 0 to 2 pi, which is 16/3 times 2 pi, which is 32 pi over 3. And we believe that is the volume of a sphere with radius 2. Let's check our work with some geometry. Volume of a sphere is 4/3 pi r cubed. We said our radius was 2. So 4/3 pi times 2 cubed, 4/3 pi times 8, which is 32 pi over 3, which again agrees with what we did with calculus.